right. Afternoon, everyone. So it's a pleasure to welcome you here for this afternoon session. So the name of the session is Heart and Backbone from Life to Industry, and who is better to connect to reflect on this than one renowned scientist and three brilliant businessmen on our panel. But before we go, we will join our exciting panel. Unfortunately, you have to listen to two talks, and looks like from the names on the panel, it's going to be mainly on carbon science, but it's very interesting that over the years the science of carbon and especially carbon nanomaterials has been driving many different businesses over in many different areas. And well, I guess we're going to talk a lot about graphene today. It started as a curiosity project, but it very quickly turned into a multi-billion operation for many different applications. So I think it really presents a very good case for science to industry translation, and I guess we will be asking our panels about this today. So I will ask for my slides to be projected, and probably just give you a little bit of the background of the kind of science what we do. It's a bit of the pretentious. So I'm acting here as a Majorana presenter here. So I'm both the moderator and the presenter at the same time. So I track my own time. So just don't get angry with me. So it's a bit of the pretentious title, but I really think that the area of 2D materials gives us a very good platform for the future applications. And it's even though we're talking about 2D materials, I think carbon-based materials and graphene in particular gives a good platform for this. It's really one of the most simplest possible material, just only one atom thick, and carbon is one of the lightest elements in the universe, and yet, despite its simplicity, it has so many superlatives, like being the thinnest possible and the strongest, conductive and thermally conductive and flexible and transparent and so on. So it gives rise to a number of possible applications, from composite materials, we're going to hear later about this, to energy. So we heard yesterday that we have our electric vehicles, they all use quite a lot of graphene these days, to electronics and optoelectronics and sensor and biosensor and so on. And so these days, surprisingly, so we passed the hype cycle, and now we're in the stage of the development of those applications, and they're coming into real life every day. So what is important to know is that even though graphene gives us a lot of fantastic science, and we're still working on this, and there are still lots of new papers appearing every week on graphene, twisted graphene, and so on. There is actually a full family of those two-dimensional materials which we need to think about, and this this family covers a huge range of different properties, from being the most insulating to the most conductive so there are semiconductors, semi-metals, there are superconductors, there are ferromagnets, and of course the physics in two dimensions is extremely exciting, because in 2+1 dimensions you have this special property of being able to twist your quasi-particles in such a way that you can create non-abelian anyons, so that you can do some quantum computation. So it's important for the future quantum computations, but it has other implications as well. And to talk about this, let me just step back a little bit and remind you that materials are fundamentally important for our technologies. We even call the names, the ages we live in, by the names of the dominant materials, like the Stone Age, the Bronze Age, the Iron Age. It's a good question. So how would you call the age we live in now? And probably for the first time in history, we have really quite a selection of the possible names. You can say maybe it's a digital age, or a silicon age, or maybe nuclear age. But what is important maybe to think, do you really need to put a name, to put a dominant material out there, and how dangerous or how important is it? Let me give you one example. So here is the periodic table of elements which we used in silicon technology prior to 1990. So really, I really love this periodic table. It's only 6 elements. Silicon is there, then boron and phosphorus for doping, p-type, n-type, aluminium for interconnects, and then hydrogen and oxygen for passivation. Brilliant. Then after 1990, we needed to shrink our transistor a little bit more. So we had to use more conductive materials for interconnects. So we started to use copper. It immediately brings a problem that copper diffuses into silicon. So you need diffusion barrier. You need some work function matching materials. We had to add, apart of copper, we had to add quite a few other elements as well, but still manageable technology. Now, because we stick with silicon and we shrink those transistors more and more, these days this technology uses more or less half of a periodic table of different elements, and it's because we don't want to change from one material to another. We stick with silicon, but we have to adapt this material for modern challenging. And it's really quite bizarre, because if you compare how many elements your body have got, it's actually we use more elements in silicon technology than we have in our body. And again, the only reason that we really want that we don't want to change the technology, we stick with the dominant material. And that's really it's quite a common problem, because once it's the nature of humans that once we have our dominant material, we tend to stick with it. So we use silicon for electronics, we use steel for construction, we use aluminium for aircraft, and it's great that we know those materials inside out, but it still limits our abilities, because every time an engineer wants to create a new device, he or she would need to change what silicon can do for me. Was the work function, was the band gap, was the band gap of silicon oxide, and then create the device within those ranges. So ideally, you don't want this. You really want to have the ability to create your device and then find a suitable material. And it's possible because we have this ability to mix and match, and it's called composite materials and heterostructures, but still there are only a few examples of this. Ideally, you would want to have the ability to design a new material specifically for your application. You would be able to nominate the top layer maybe for sensors, then so that a few layers for solar cell, a few layers for logics, and so on and so on and so on. And 2D materials, so this one atom thick fabric, they actually have got this exactly this ability because you can construct artificial materials from scratch, just putting one layer of one material, one layer of another material, and just building up those crystals as you want in order to create artificial three-dimensional structure which can perform exactly the functions which you want for your device. So it has been available for the last few years, and people really created a number of unique heterostructures, including those for applications. So in this case, so this is the light emitting diode. So you just so graphene plays on the secondary role here. There are many other materials which are important here, but you can make transistors, you can make resonant tunneling diodes, you can make solar cells, you can make light emitting diodes. You can do so really lots of new materials. But what is exciting that this situation is not just simply linear. So you really got new physics out of it. So you can. I'll probably skip it. It's a beautiful picture, which I have no idea how to describe in 30 seconds, but I just say that if you there is new emergent physics that if you take two perfectly conductive graphene sheets and you just put them together and you rotate by a small degree, you can turn it into an insulator, and or if you apply voltage to it, you can turn it into a superconductor. So or if you take 1 + 2 layers, you can turn it into a ferromagnet. So really, the emergent physics which appears from here is extremely rich, and that's exactly what we expect from our science. And I should say that so this is the Manchester data. The previous slide was from Pablo group in MIT. So what just before I finish, I want to say a few words about the new era which is coming to us, about the application of artificial intelligence for the materials design, and people have been working on this and speculating on this for the last 2-3 years. And 2D materials actually are quite is a nice platform for this, because of course you can create 3D materials by stacking those together, which is frankly too complex, not only for humans but also for for artificial intelligence. But it also got this it gives you this opportunity that you can change the chemical structure in the plane, which is because it's a rare case when your material is so the bulk of the material is at the same time as the surface, and it gives you opportunity to modify it quickly and change the property and study this. And of course, we thought it would present perfect case for the application of the artificial intelligence to design the new properties of those 2D materials. So we created lots of databases, so both in our group, but those exist globally, and so we tried to do it, and we failed miserably. So and I should say I mean, it was a bit painful that we failed, but at the same time, we feel that we are in a good company, because many other groups did fail as well. So here is the example of the famous Google DeepMind paper from 3 years ago, when those guys, after the success of ChatGPT, they thought you can apply artificial intelligence to pretty much anything. Everybody thought about this, and they thought that they applied it for the materials design. So they calculated more than 2 million different materials, identified that almost 400,000 of those would be stable, tried to synthesize about 50 of them, managed to synthesize 43, and none of them turned out to be new. So, and this is a really common, a bit of a common problem, that the artificial intelligence, which we saw works beautifully for language translation, for the generation of the new text, doesn't work at all in some of the areas of science, like in materials design. And one of the reasons for that is that the databases which we use are based on very, very simplistic materials. They have just a few atoms in their unit cell. At the same time, when we think about materials which we use in our everyday life, we don't use those pure materials. So even iron, we don't use iron. We use steel, and steel is usually alloys. So you put some chromium, some carbon into it. So your unit cell immediately gets huge. Even worse, you don't use the useful properties are coming not only from the chemical structure. They're coming from the morphologies, from the grain structure of the crystallites and so on. And then for some of the applications, for example, for catalysis, we have to structure them into the three-dimensional shape and so on. If you take silicon, it's exactly the same problem. You don't use silicon, you use the doped silicon, then you structure it into p-n junctions. You structure them into the transistors itself. So I really believe that we have some new opportunities in terms of the applications of AI for the design of the new materials. But we have to rethink this cycle. We shouldn't go blindly from material structure to the material properties. We have to think about the synthesis as well. So we have to really put more efforts into the synthesis of the materials and learn how to synthesize those new structures and with the new properties. And that's exactly what people are doing these days. So they study the synthesis properties, the trees of the possible synthesis chemical reactions, and then they educate their structure. So in that sense, I'm not that skeptical. I'm not that pessimistic, but I think that there is a lot of work still to be done in terms of the applications of AI for the materials design, and it will be the basis for many new scientific discoveries, but also for the applications as well. So with this, I will stop, and I will pass the baton to Rahul, who is going to talk much more focused, hopefully, about the materials and the applications for a variety of different industries. Rahul, please.
Good afternoon, everyone. First of all, I would like to thank WLS for inviting me for this event. Thanks, Kostya, for introducing my talk as well. Today I will be talking about graphene membrane. So it's basically from materials to impact, graphene membrane for net zero water treatment. So I'm from the University of Manchester. We have the graphene capability, research capability from very low TRL, like TRL 1 to 3 at the National Graphene Institute, to the higher TRL, which is Graphene Engineering Innovation Center, where we do high TRL research in collaboration with industries. So when you say graphene, especially it's a single layer of carbon atom, thinnest material and so on, in terms of as a membranes perspective, this is the best membrane we can think about because it is the thinnest material, the transport resistance is so small, and we can tune the material to create membranes of pore size or properties, whatever we need. So there is a great properties of enhancing or tuning the property. But if you think about practical applications, there are even more opportunities, not just using a single layer of carbon atom, but we can assemble different 2D materials, including graphene or functionalized graphene, into creating much more 3D-like or practically usable device or membrane. So for this example, we assemble graphene oxide, functionalized form of graphene, into a layered or laminar structure, and then control the distance between the layers to tune the pore size, or control the chemical functionality of each layer to control the selectivity of the membrane. Such membrane, typically they are impermeable to gases but permeable to liquids. So once when you expose to gases, these layers are tightly packed, nothing can go through, but when you expose to vapors or liquid, it self-expands, it's called membrane swelling, and liquids goes in between the layer and permeate. And the selectivity is controlled by the distance between the layer, and we call it an adaptive membrane because depending on the environment to which it is getting exposed, the properties can change. So we were working for such membrane for more than a decade now, from small scale now to a large scale. And membranes are not just limited to graphene oxide. We can develop such membrane based on different materials like graphene, graphene oxide, clays, example is vermiculite, molybdenum disulfide, even now mexene, and so on. All of these materials are processable in liquids, like you can make a graphene oxide in water, mexene in water, MOS2 in water, and so on. And then you create a membrane. It looks like a piece of a paper basically, and it has a very nice layered structure, and the molecular transport again occurs between the layers. So we started, of course, with small scale of membrane. Now in lab, we can scale it up really. So that is the beauty of this technique, this chemical method of producing 2D material. So these are the pictures of large scale membranes what we make in the lab. So first one is a hollow fiber. First two of them are hollow fiber membranes. So basically you take a polymer tube, then you modify or coat that with any of this 2D material. The coating can be inside or outside. So that is what you see in the middle picture is a scanning electron microscope. The active layer, which is around tens of nanometer to hundreds of nanometer, it's a tunable, and that gives all the selectivity to the membrane, and the substrate, that's the bottom layer, is a porous polymer. Same thing can be also applied to the desalination membrane, which is not hollow fiber, which is spiral wound membrane. It's just basically you make a piece of paper and then spiral it into making large area membrane. Now, if you look at in terms of performance, you can see all the open doors that are from graphene-based membrane. The flux is orders of magnitude higher than the solid data points are from the commercially available membrane. And with graphene, the beauty is again we can control the pore size from tens of nanometer down to even sub-nanometer by tweaking the formulation of the material or changing the functionality of the material and so on. Now, if you are specifically interested in water desalination, seawater desalination, that is a comparison of a data what we created in our lab. So the red data is from graphene-based membrane for seawater desalination, and the black one is the state-of-the-art membrane which is available in the market, which is called a Toray membrane. That is the best membrane at the moment we can buy. So that data is specifically on a fouling. So in terms of water filtration, is a technical term. Salt rejection is you get 99.9% even with commercial membrane. Graphene can get the same. So but the real benefit is in the lifetime of the membrane. It's called membrane fouling. So the data is from a biofouling. So if you look at the membrane performance as a function of time, the Toray membrane decreases the water flux with time, but graphene, yes, there is a slight decrease, but it stays there. It's mainly because it has a self-cleaning capability. So the foulant does not stick to the surface. If you because of the cross flow, water is flowing through the membrane, that can keep the membrane surface cleaner. So that means we can extend the lifetime. So these all are Now we are comparing graphene membrane with the existing membrane in terms of performance. We are improving the performance, improving the lifetime and so on. But with graphene based membrane, we can do even much more than what commercial membranes can do. So in terms of a long term perspective, this is a concept we published several years back on smart membrane. So graphene based membrane, we can make it electrically conducting by creating certain conducting filament, and by controlling the current through such membrane, we can make it even a smart membrane. So by passing a current, the water flux through the membrane can be controlled from on state to off state, or even precisely controlled in between. For example, you see that it can multiple times switch on and off by applying a current. Water either goes through or gets stopped, or you can switch off the membrane for a longer time by applying a current through the membrane. So that's a concept for smart membrane, but this is definitely at the low TRL. This is a proof of concept experiment we did several years back. Now if you think about something what we can do more in a short time, we were thinking about water desalination. But now if you think about water desalination, what I was showing in the previous slide was improving the membrane in terms of fouling, or improving in terms of water flux and so on. But again, we are using the current process, what is called reverse osmosis process for water filtration. So the scope for improvement there is maximum 10% or so in terms of, if you look at the energy intake by looking at the fundamental process. Desalination, if you think more closely, you can see that desalination produces clean water as a product, but it makes three other problems for us. The three problems are it is a high energy intensive process because you have to overcome the osmotic pressure. That's, if you look at its terawatt of power globally it is using, and it creates 100 million tons of CO2 as an emission just from the RO process. And more than that, typically the recovery means if you take a seawater, only 50% of that get maximum. It's typically 40 to 50% is converted into pure water, and the rest of the water is going back to sea as a brine, highly concentrated seawater. So that is actually causing a lot of ecological problems and so on. So the current technology create one product, but it's creating three problems for us. So we were thinking, can we redefine this process, RO itself, by using this kind of wonderful material, graphene-based material. So now if you think about the current process, there are three methods of doing desalination. This is very fundamental physics, like reverse osmosis, forward osmosis, membrane distillation. So in reverse osmosis, we apply a pressure, mechanical pressure, to overcome the osmotic pressure, that is delta pH in the bottom equation. If you think about forward osmosis, we apply an external high concentrated saline water, that's called draw solution, that creates a delta pi chemical potential gradient or osmotic pressure gradient to drive the water. Or if you think about distillation, that is delta T, we create an external temperature gradient. So either external temperature gradient or concentration gradient or pressure gradient is required to pump the water from seawater to the pure water, or just to overcome the osmotic pressure. So this is the current state of the art processes. Now if you think about our biological membranes, for example in our body, lot of kind of reverse osmosis or membrane or ion transport, water transport, all occurs in our body and all in plants and so on. But in all that process, there is no external temperature or no external pressure, or there is no external concentration gradient is there. So in that process, most of the time, the water transport occurs by using the cellular energy, and this energy is deriving from chemical reactions basically. So we were thinking, can we create or mimic something like that by using 2D materials? Can we create the energy from chemical reactions to drive the water transport? Now if you think about our membranes or graphene, they are actually 2D capillaries. And if you think about such a capillary with a negatively charged surface charge on the membrane, and if you put it in water, typically it forms electrical double layer. And because of the negative charge, if you put an external ion into the membrane feed, the same charge, ion with the same, we call it co-ion, that cannot enter the membrane because of the electrostatic ion exclusion. This is also known before, ion exclusion phenomena. Because of the same charge, ion cannot enter because of electrostatic repulsion. Now we think little bit differently. We think, okay, can we somehow create this ion inside the channel, a negative ion, a co-ion inside a negatively charged capillary? And if that is the case, these ions are not stable because of the electrostatic repulsion, they should come out from the channel immediately. And if ions are coming out, that create an osmotic pressure, and ion also will drag the water out of the channel, and that is a possibility of taking water out from the such capillary. And in this process, there are three interaction-driven pressures are existing that drives the water. One is electrostatic repulsion, which actually repelling the ion from the capillary. Second one is van der Waals attraction force between these graphene layers. And third one is osmotic pressure, which is directly proportional to the number of ions coming out. If you take more ions, of course, more osmotic pressure will drive the water out. So this is what experimentally we did now, and such a experiment, if you can continue long, so like continuously run the ion creation inside the channel, that will drive water out from the capillary continuously as well, and it is a non-equilibrium process, and then we will get a continuous process in practice. This is what exactly we did in experiment. So we take a graphene oxide membrane, which they are negatively charged, and one side of the membrane we take an alkaline solution, like we add some potassium hydroxide or ammonia hydroxide. Other side of the membrane we added a carbon dioxide gas. So one side of the membrane is alkaline water, other side is carbon dioxide. These membranes are impermeable to gaseous CO2, but carbon dioxide can dissolve in water and little bit penetrate inside the membrane, and such a reaction happens inside the membrane. So KOH plus CO2 create a bicarbonate. Bicarbonate is an anion. So once anion is there, they are electrostatically unstable, it comes out, and water should come immediately out as well. That's what our idea was. And so such process to occur, there are three conditions we need. The membrane has to be highly negatively charged. Because of negative charge, it also excludes all the anions except OH minus ion, because we need to have that reaction inside. And the channel size should be 1 nanometer or as minimum as possible to get this phenomena maximum. So experimentally again we tried, and this is what exactly we see. You take a membrane, put it in a hydroxide only on one side, other side is air or CO2, and immediately what we see is that liquid water is coming out of the membrane, and you can see big droplets. And if you wait for some time, if you say, let's say 1 centimeter square membrane, you get tens of milliliter of water by waiting several hours. So this is no pressure, there is no chemical external gradient. Only thing is we have an alkaline water on one side and other side is air or CO2. If you remove the air or CO2 with, let's say, nitrogen or argon, no liquid comes out. So this membrane surface is dry. As soon as you put, let's say, few percentage of CO2, even air is fine, you get this big droplets of water coming out. It's not really pure water, it's a carbonate water. It's a carbonate or bicarbonate. So now, thinking about applications, so we started with the alkaline water. So what about alkaline seawater? So we take seawater and put some ammonium hydroxide in this case to make it alkaline, and we see that the permeate, which is carbonate, that is free from chloride, but on the return date, which is the water left in the feed, that is actually rich in chlorine. So we are actually partitioning the sodium chloride into sodium in one side and rich in chloride on the other side. Now if you think about the current reverse osmosis process, so what we do is we're taking a membrane and taking water out and keeping all the sodium chloride in one side. So basically you keep the sodium chloride and getting water. So but this process, you are partitioning the sodium chloride into sodium on one side and chloride on the other side. Sodium becomes sodium bicarbonate, and chloride become, if you are using ammonium hydroxide, it becomes ammonium chloride. So that is the difference between this process and the current process. And then the bicarbonate liquid what we generate can be using some ion exchange process. We can get back all the carbon dioxide back and then water. So bicarbonate become CO2 and water. And then if you think about the whole process, we start with sodium chloride and ammonium hydroxide in the feed, some flue gas which is few percentage CO2, and that generate ammonium chloride, sodium nitrate. Again, nitrate is coming from an ion exchange process, and pure CO2 that is during the again ion exchange process, and water. So there is no waste is generated in such process. All the products what we are generating, ammonium chloride, sodium nitrate, they are actually fertilizers. And pure water and CO2 again is a value added product. So from what we need is a CO2 gas and ammonium hydroxide as a feed. So that means we are generating value during the process rather than creating problem compared to the seawater desalination. So we call it the near zero liquid discharge. That means there is no brine is generated. Sodium chloride is not generating in this process, and we are creating value by creating ammonium chloride, sodium nitrate fertilizer. And it is also scalable by using a hollow fiber membranes. Now, if you think about the state-of-the-art RO process, they are using spiral wound membranes. So here we are using hollow fiber. This is a simple process and no external pressure and so on. Now, just for a comparison, if you take a 1 liter of pre-treated seawater, and during this process, what we generate is half a liter of potable water, then half a liter round of a liquid fertilizers and pure CO2. That is the whole process, and we are now commercializing this technology by using a spin-out from the university called Holograph Limited. With that, I conclude. So we say the graphene-based membranes have a great potential in RONF membrane. That's basically improving the performance. But more than that, we can also design a new novel process to completely redefine the existing reverse osmosis process for energy-efficient water filtration. With that, I can acknowledge all my team members, collaborators, and more than that, Professor Andre Gaim and Professor Kostya Navasale for motivation, guidance, supervision, and much more. With that, thank you very much.